Trajectory control for differential drive mobile manipulators is a complex task due to nonholonomic constraints and dynamic interactions between the manipulator and mobile platform. Mobile manipulators, comprising a mobile platform and a manipulator, offer increased mobility and dexterity compared to fixed-base manipulators. However, they pose challenges in decomposing tasks into fine and gross motions, establishing a dynamic model, and controlling the system to avoid tipover. The Fetch robot, a differential drive mobile manipulator, is used to validate the proposed method. This robot consists of a 7DOF manipulator mounted on a mobile base, enabling it to perform pick-and-place tasks in an indoor warehouse environment. The project's major contributions include deriving the system's dynamics using Lagrange's method, trajectory planning for the manipulator and mobile base using the TrackIC package, implementing a state machine for the pick-and-place task, and solving the inverse kinematics of the manipulator. Differential drive systems are sensitive to slight changes in velocity and cannot move in the direction along the axis of singularity, making control challenging. To address these challenges, a control method is developed for manipulators mounted on mobile robots, applicable to large manipulator motions with limited sensory information. The results indicate successful implementation of trajectory control on the mobile base and manipulator of the Fetch robot. This research aims to develop a comprehensive approach for computing actuator commands for mobile manipulators, ensuring they follow desired end-effector and platform trajectories without violating non-holonomic constraints. The proposed method provides a novel solution for controlling differential drive mobile manipulators, enabling them to perform complex tasks in various environments. Mobile manipulator control is a complex challenge that requires synchronizing the movement of a mobile base and a manipulator arm. To address this, researchers have developed a planning algorithm to find an optimal path from a start position to a goal position in a simulated environment. This algorithm is integrated with a state machine designed for a pick-and-place task, which is then tested using the Fetch robot in a simulated environment. The significance of this approach lies in its potential to enhance trajectory planning and control in warehouse domains, where picking and placing objects efficiently is crucial. Moreover, the methodology can extend the autonomy of service robots, enabling them to perform complex tasks with greater precision. Previous studies on mobile manipulators have investigated dynamic and static stability, force development, and control in the presence of base compliance. For instance, Alicia et al. Presented a dynamic control algorithm for holonomic systems, while R. Solea et al. Proposed a methodology for generating trajectories using nonlinear sliding mode control. Ide. S. et al. Developed real-time trajectory planning using model predictive control with constraints, and Dong et al. Created a global tracking controller based on the dynamics of the defined tracking error. Koream et al. Proposed an open-loop optimal control method for trajectory optimization of flexible mobile manipulators. However, previous approaches have limitations, including the lack of consideration of system-specific parameters and high planning times in certain methods. In contrast, this research focuses on the Fetch robot's specific parameters, avoiding generalizations that may not be applicable to all manipulators. By considering these system-specific parameters, the proposed approach can provide more accurate and efficient control of mobile manipulators. Inverse kinematics, a well-established research field, continues to elude a universal solution. Prominent approaches include geometric analytical solutions and iterative optimization methods. Notable methods involve computing the Jacobian using the transpose, pseudo-inverse, or damped least squares method. However, these methods can become stuck in suboptimal extrema depending on the kinematic model's geometric complexity. Constructive approaches, such as TRACIK, overcome this issue by performing heuristic restarts from random initial configurations. TRACIK, a novel method publicly available under the ROS framework, has been shown to significantly outperform the classical ArXiv KDL solver. This work consists of 5 modules: writing the system dynamics, trajectory planning, inverse kinematics, finite state machine for the pick-and-place task, and trajectory control using PID. The system dynamics involve writing the Denevit-Hartenberg (DH) parameters for the manipulator arm. These parameters, consisting of 4 parameters offset along previous z to the common normal, angle about previous z, length of the common normal, and angle about common normal, enable transformations between frames. These parameters are calculated for the fetch robot, as the URDF file was inconsistent with the DH convention. The transformation matrix is then computed from the DH parameters, providing the forward kinematics of the system. Differentiating the transformation matrix with respect to each joint angle yields the Jacobian matrix, relating end-effector velocity to joint velocities. The pseudo-inverse of the Jacobian matrix is computed to obtain joint velocities from end-effector velocities, as described in equation 1. This equation is crucial for solving the inverse kinematics problem. The velocity Jacobian, denoted as J, computes end-effector velocities from joint velocities, represented as underscore. The kinetic and potential energies of the fetch robot system are calculated from joint velocities and robot parameters. The Lagrangian, L, is the difference between kinetic energy, K, and potential energy, P. Torque, tau, is computed from the Lagrangian using the equation tau equals d, dt. Partial differential L, underscore, partial differential L, partial differential. This torque equation yields the inertia matrix, M, Coriolis matrix, C, and gravity matrix, G. The state space form of the system is M, Q, Q plus C, Q, underscore Q, underscore Q plus G, Q, equals tau. Transformation from the robot base to the end effector is obtained using the joints of the fetch robot, as shown in Figure 4. Trajectory planning for the manipulator involves point-to-point motion for each of the 7 joints, subject to position, velocity, and acceleration constraints to avoid discontinuities in acceleration, which can lead to impulsive jerk and reduce tracking accuracy. A quintic polynomial trajectory planning is used to satisfy these constraints, resulting in a fifth-order polynomial equation Q, T, equals a 0 plus a 1t plus a 2t squared plus a 3t cubed plus a 4t⁴ plus a 5t⁵, where t is the time of execution of the trajectory, and a0, a1, a2, a3, a4, a5 are the coefficients of the quintic polynomial. The goal is to find a trajectory connecting an initial to a final configuration while satisfying endpoint constraints. Equations for initial and final position, velocities, and accelerations are given by equations 510. Representing these equations in matrix form allows computation of the polynomial coefficients if the time of planning for each joint is known. This determines the position, velocity, and acceleration for each joint. The high-level control for trajectory planning and control of the manipulator is shown in Figure 5. The high-level trajectory plan is generated using the quintic polynomial trajectory for each joint, and a PID controller for each joint follows the trajectory generated by the quintic polynomial. The PID control law is given by equation 12, and the torque is given as feedback to the control law as defined in equation 3. The trajectory planning for the mobile base in this project is performed using the A algorithm, a widely used search algorithm in pathfinding and graph traversal. This algorithm traverses the graph following a path of the lowest known cost, utilizing a heuristic to focus the search towards the most promising areas of the search space. The priority queue is based on F equals G plus H, where G is the backward cost and H is the forward cost to the goal. For the A algorithm to give an optimal solution, the heuristic should be admissible, meaning it should never overestimate the true cost to the goal. The path returned by the A planner is then time parametrized before being passed onto the controllers. The error term for the controller is the Euclidean distance between the time parametrized path from the A planner and the actual path followed by the mobile base. This error term is used in the control equation, equals Kp tilde Q plus Kv tilde Q plus kist, where Kp, Kv, and K are the position, velocity, and integral gains, respectively, and tilde Q is the error term. Inverse kinematics is performed using the TrackIK package available in the ROS framework. TrackIK is an enhancement of the KDL's pseudo-inverse Jacobian solver, which improves performance drastically. The TrackIK solver addresses issues with the KDL solver, such as the need to provide a maximum number of iterations, which can be difficult to determine. Instead, the user provides a maximum time allowed for solving, and the solver dynamically determines the number of iterations. The inverse Jacobian IK implementations can get stuck in local minima during the iteration process, particularly when joints have physical limits on their range. To mitigate this, the track IK solver detects local minima and changes the next seed. However, this method does not handle joint limits well. An alternative approach is to solve IK using sequential quadratic programming, SQP, which can handle constraints like joint limits. The SQP problem is formulated as a nonlinear optimization problem, minimizing the overall amount of joint movement while considering Cartesian error as a constraint. The SQP method uses dual quaternion error as a combined measure of distance error and angular error in Cartesian space. However, generating the dual quaternion error can be computationally expensive. An alternative is to use the sum of squares metric, which is faster to compute. The track IK solver uses both SQP and KDL solvers in parallel, and returns the solution from the first solver to finish. This approach is used in the project, and the results for the IK solver are discussed in a later section. A finite state machine, FSM, is employed to model the pick and place task using the fetch robot. The FSM, an abstract machine that can exist in one of a finite number of states, transitions between states in response to external inputs. Defined by a list of states, initial state, and transition conditions, the FSM checks the robot's status to determine the location of the base and end-effector, invoking different parts of the system to facilitate task execution. The fetch robot serves as the implementation platform, with its kinematics specified by the robot's Unified Robot Description Format, URDF, model. The URDF model describes the attributes of the joints, links, and frames of the robot, including inertia, visual features, and coordinate frames. The Denevit-Hartenberg, DH, parameters and system dynamics derived earlier are used to populate the URDF model. The coordinate frames for all links in the fetch and freight are defined with a positive z-axis up, positive z-axis forward, and positive y-axis to the robot left when in the home pose. Joint position and velocity limits are enforced for all joints, serving as constraints during trajectory planning and inverse kinematic solution finding. The fetch robot is equipped with various sensors, including a SICK-TIM 571 scanning rangefinder, a 6-axis inertial measurement unit, IMU, PrimeSense short-range RGBD sensor, and a gripper sensor. The laser rangefinder has a range of 25 meters, 220 degrees field of view, 15 Hz update rate, and angular resolution of 1/3 of a degree. The IMU's gyroscope measures plus 2000 degrees per second, while the accelerometers measure plus 2 grams. The gripper incorporates a 6-axis IMU and provides position and effort feedback. The entire task is performed in a ROS gazebo simulation environment with the fetch robot. The system dynamics derivation began with formulating the DH parameters for the manipulator of the fetch robot. The derived DH parameters are validated by performing forward kinematics in MATLAB. The simulation world is created in Gazebo, with the fetch robot and environment modeled. The world environment is formed by placing models of the shelf and object in the Gazebo world, and the fetch robot is spawned into this world by importing its URDF file. The simulation environment is visualized in Figure 8, featuring the fetch robot, shelf, and object within the Gazebo world. Upon movement of the robot's base, inverse kinematics is performed using the track IK solver within the ROS framework. This solver outperforms classical solvers, such as Oraco's KDL, with an average solution time of 0.44 milliseconds and a higher success rate. Trajectory planning is subsequently carried out for both the manipulator and mobile base of the fetch robot. For the manipulator, planning is executed in joint space, considering joint limit constraints to avoid the need for inverse kinematics at each planning instant. This approach saves considerable time and avoids the complexity of obtaining correct joint angles from multiple inverse kinematic solutions. Position, velocity, and acceleration profiles for one of the joints are shown in figures 10 and 11, with similar profiles obtained for all joints. Quintic polynomial planning is employed to minimize jerkiness in the system. For the mobile base, trajectory planning is performed using the A-path planning algorithm. The algorithm is first tested on a PR2 robot in the Open Rave simulation environment, generating paths for 4 connected and 8 connected spaces using Manhattan and Euclidean heuristics. The results demonstrate the superiority of the 8 connected Euclidean heuristic, with a lower cost and fewer nodes explored. The path generated by the A-planning algorithm for an 8-connected space with Euclidean distance heuristic is shown in Figure 9. The parameterized path found by the A algorithm is published on a topic, to which the base of the fetch robot subscribes, enabling its movement. This approach allows for efficient and effective trajectory planning for both the manipulator and mobile base of the fetch robot, facilitating smooth and precise movement within the simulation environment. The research paper discusses the implementation of a pick-and-place task using the fetch robot, which involves both trajectory planning for the manipulator and mobile base, as well as controlling the gripper action. To achieve this, the authors utilized a state machine in C++ that automates the entire process by transitioning between different states upon receiving ROS messages after completing previous tasks. The paper begins with the transformation between the base frame and odometry frame, using the TF package available in ROS to find and record the transformation. This transformation is crucial for moving the robot base to the desired location according to the planner's output. The authors then describe the implementation of a PID controller for both the trajectory planning of the manipulator and the mobile base. The PID controller ensures that each joint follows the generated trajectory by minimizing the error between the desired and actual joint positions. The controller gains are tuned to ensure system stability. For the mobile base, the PID controller minimizes the Euclidean distance between the time parameterized path from the A planner and the actual path followed by the mobile base. The paper also presents the joint trajectories, velocity profiles, and joint efforts for each joint in figures 12, 13, and 14 respectively. These figures demonstrate the effectiveness of the trajectory planning and PID control in achieving smooth and precise movements of the robot's joints. In addition to the trajectory planning and control, the authors implemented a state machine in C++ as a ROS node named fetch_trajnode. This node automates the entire pick-and-place task by executing tasks sequentially according to the predefined flowchart. The state machine transitions between states upon receiving transition requests in the form of ROS messages after completing previous states. Finally, the paper discusses the control of the gripper action, which involves commanding the gripper to a fully closed or fully opened position with specified effort. The gripper command takes in position and effort as parameters, and the grasp strength is determined by the maximum effort. To pick up objects, the authors controlled the effort generated by the gripper in the fetch robot. The paper concludes with the TF tree and RQT graph showing the transformation from the base frame to the odometry frame, as depicted in Figure 15. This transformation is essential for the successful execution of the pick-and-place task. This project successfully implemented trajectory control for the fetch robot, a differential drive mobile manipulator, in a simulated environment. The implementation includes dynamics of the fetch robot, trajectory planning for the manipulator arm using a quintic spline, and mobile-based trajectory planning with the A-planning algorithm. A state machine for the task of indoor warehouse object manipulation was developed, and the TRASIC package was utilized for performing inverse kinematic calculations. The results of the experiments are presented, demonstrating the achievement of the project goals stated in Section I, following the methodology shown in Section 3. Future work includes developing a global planner that can autonomously determine the mobile base movement and end-effector placement, making the trajectory control package open source, and implementing the system on an actual hardware platform in an indoor warehouse environment. Additionally, incorporating computer vision techniques to enhance the state machine and making the different aspects modular for easy portability are planned. The authors acknowledge the guidance and support of Professor Eugene Eberbach and Junius Santoso. The paper cites 16 references.